Next example is, it's very important. So every cyclic group is isomorphic to set of integer or z by generated by n. So this is z by n. Now this is very important result. So if cyclic group is of infinite order, then it is isomorphic to Z. If it is a cyclic group of order n, then it is isomorphic to Z by n. So these are two parts. One is when it is of order n, and second it is a of order infinite. So we will discuss as a two part. So first I will take as G is infinite cyclic group. So first part, so let G is generated by some A be a cyclic group of infinite orders. Infinite order. It means there exists no least positive integer n which satisfy a raised to power n is equal to identity. So this is of infinite order. So first case. Now in this case, define a map from Z to G. So what is the element of G? So first check the element of G is of the kind that is equal to a raised to power n. So element of G is this a raised to power n, and n belongs to set of integer. So this is a element of this. Now define a map. So define a map f from Z to G, and this is defined by f which is of n and a raised to power n for every n belongs to set of integers. So this is equation number 1. Now in this case, Z which is a set of positive integer, so it is a additive group of Z plus, it is a additive group of integers, and G is a multiplicative group. So remember here, so here the binary composition is plus, and here the binary composition is multiplication. So remember that. Now to prove this mapping is already, it is a well-defined map. So to prove it is a homomorphism, so I take M and N. These are two elements from the Z. Now left hand side the binary composition is plus. So I use M plus N. So this will become a raised to power M plus N. So this can be written as a raised to power m into a raised to power n. So this value can be written as f of this values f of m into f of n. So here it is, this group is with the binary composition multiplication. So this can be written as Fm into Fn. So it implies my first step, F is homomorphism. So F is homomorphism. Now next step is that this mapping is onto. Now we know that in the cyclic group, the order of group G and order of element are same. So in the cyclic group, order of G and order of generator are same. So since order of A and order of G are same, and what is this? It is a infinite. So if it is a infinite, then it means there exists no positive integer n such that a raised to power n equal to identity. So it means a raised to power n equal to identity if and only if n equal to 0. So this is because of infinite order. So that is my given part. Now to prove it is a onto map, so I will take some y which is from right hand side, that is from G. If y belongs to G, then what it means? The element of y is equal to a raised to power n. So it implies this y is equal to a raised to power n for some integer n. So it implies this values, this y which is equal to a raised to power n. By definition, this value is equal to f of n. So by definition, this value can be written as f of n. If this value is equal to f of n, then it means this value is f of n. Then it means for every y belongs to G, there exists a n belongs to Z such that f of n is equal to y. So it implies this mapping f is a onto. So in this way we can prove that this mapping is a onto. So from this what we get? We get this mapping f is a onto. Now next is 1 1. Now to prove it is a 1 1, so we have two ways. One, kernel of f consisting only identity element, and second f x equal to fy, it implies x equal to y. Now kernel of f. Now what is kernel of f? Let some element x belongs to kernel of f. So what is kernel of f? So this is consisting only those element. This is consisting only those element whose image is equal to identity. So this consisting only those element whose image f of n, which is identity of G, so which is equal to E, this values. So if I take x, ja, n, any number, so I take here n. So it implies f of n which is equal to identity. So what it means? It means a raised to power n, this value is equal to identity. If a raised to power n is equal to identity, by previous part, so a raised to power n which is equal to identity. So by, since this is a infinite order, so it implies n equal to 0. So it implies this kernel of f, it consisting only 0 element. If 0 element, then it means f is 1 1 mapping. So f is 1 1 mapping. So f from Z to G which is a homomorphism, 1 1 as well as on 2. So what it implies? It implies this Z which is isomorphic to G. So we can say that this G is isomorphic to Z. So when it is of infinite order. Now second part. In the second part, now G is a group of a finite cyclic group of finite order. So in the second part, let G be a finite cyclic group of order n. So of order n. So what it means? So it means G is generated by some values, that is A, and order of G and order of A is equal to n. So in this part, order of G, so this is order of G, order of A. So what is this? Which is equal to n, this values. So by definition of order, so n is least positive integer such that a raised to power n is equal to identity. So remember the definition of order of A. Now after that, when we prove this result, here my aim is to prove this is a this Z is G is isomorphic to Z by generated by n. Now again I define a map, same, I define a map F. This is from this G to Z to G. So again I define a map F from Z to G. So if I define a map Z to G, so I define a map again from Z to G. So this is by f of n, which is equal to a raised to power n. So on similar line of action, we can prove that it is a homomorphism. So to prove it is a homomorphism, I repeat it again. So f of m plus n, which is equal to a raised to power m plus n. So this can be written as am a raised to power n. So this can be written as f of m into f of n. So it implies this map f is a homomorphism. If f is homomorphism, so next step is to prove that it is a onto, homomorphism. So next step is to prove that it is a onto. So to prove it is a onto, I take a element from the right hand side. So when we take the element from the right hand side, so this is, let x which is equal to belongs to z, g. So it implies this x is equal to a raised to power n. So this can be written as f of n for some integer, n. So it implies what we get, this map f from z to g, this map is homomorphism as well as onto. Homomorphism as well as it is a onto. So here we will apply the fundamental theorem of homomorphism. So this map is and onto. Now, by fundamental theorem of homomorphism, right hand side G is isomorphic to Z by kernel of F. So now my aim is to prove that kernel of F is our claim, kernel of F which is equal to generated by n, right? So I take some element n belongs to kernel of F. It implies f of n which is equal to identity, and it implies a raised to power n which is equal to identity, this values. Now from this, if I take not, I am taking m elements. So this is a m element. So this is a m element. It implies order of A divide m. So it implies n divide m. So it implies m is multiple of n. So this can be written as ns, where s is some integer, right? So this can be written as multiple of n. So it implies m belongs to generated by n, because this subgroup contains element multiple of n. So m belongs to these values. Now reverse the process. When we reverse the process, we get kernel of f is equal to generated by n. So which prove our result. So it implies G is isomorphic to Z by generated by n, right? So this is my result. So if G is cyclic group of order n, in that case G is isomorphic to Z by generated by n, or if G is cyclic group of infinite order, so in that case G is generated by Z. So this is isomorphic to Z. So which prove our result. So this is very important type. So many time it is asked in the examination. So do it very carefully. Now after going to this example, now next example is prove that two cyclic group that is related to this question. So prove that two cyclic group of same order are isomorphic. So what is next question? Prove that two cyclic group G and G dash are of same order are isomorphic are isomorphic. So again this is very important question. So this question is in Guru Nanak Dev University JNDU 2001. So this is in 2001. So we already proved the previous result. So this question is related to that problem. Now two cyclic group. So let G and G dash be a cyclic group of same order, cyclic group of order n, then it implies this G is isomorphic to Z generated by n and G dash is isomorphic to Z generated by n. So that is by previous question. Now since isomorphism are equivalence relation, so it hold reflexive, transitive and symmetry property. So by using that property we know that G is isomorphic to Z generated by n and Z by generated by n, which is isomorphic to G dash. So here I am using symmetry property. So from these now using transitive property, so G is isomorphic to G dash. So that is in case of finite order. Now second case, if these are cyclic group of infinite order. Now this is of finite order. If our question, our group has infinite order. So to prove in case of infinite order, cyclic group of, so this is in this way. So remove that. So this and this. Right. Now, let G and G dash be a cyclic group of infinite order. Now, in this case, infinite order. Again, by previous result, G is isomorphic to Z and G dash is isomorphic to Z. Z is set of group of integers. Now by using the symmetry property, now since G is isomorphic to Z and Z is isomorphic to G dash, so from this it implies G is isomorphic to G dash. So in this case, any two cyclic group of infinite group are isomorphic. So in this way, we can prove this result. So this is very important result and related to previous question. Now, next part is prove that. So next is prove that statement of next question. Any finite cyclic group of order n is isomorphic to Zn. Is isomorphic to Zn. What is Zn? Zn is the group of modulo n. So this Zn consisting element 0, 1, 2, so on up to n minus 1. So what is this? It is a group of integer. So group of integer modulo n. So this is again very important type related to previous question. So in the previous question, we know that Z is related to Z by Zn. Now here it is a finite cyclic group of order n. So solutions. So let G, which is a generated by A. So this is a finite cyclic group of order n. So this is finite cyclic group of order n. So it implies order of G and order of A, which is equal to n. So this is equation number 1. Again, we can use the property of order of A. So it means there exists simply n is least positive integer such that a raised to power n equal to identity. So I am writing all the two property here. Now what is G? So G is generated by A. So it has element of order n. So it has element E, comma A square, so on, a raised to power n minus 1. So this values. So what is Zn? So this is a 0 modulo n. So Zn, which is a 0 bar, 1 bar, 2 bar, 3 bar, and so on up to n minus 1 bar. So also it is also written in term of bar. So Zn, so this is a modulo n. Now define A mapping. So clearly this mapping is 1, 1 on 2 and isomorphism, clearly. So I define a map F from Zn to G, and this map is defined by f raised to power f of n, which is equal to a raised to power n. So here don't write n, because I am using n here. So here I write m ja r. So if I write f of m ja f of r, so if I write it is f of r, so this is e raised to power r, where what is r? Where r is lies between less than n greater than equal to 0. So this is a just like a remainder when n is divided the any integers. So this is of this kind where r is lie between these values 0 to 1, 2, 3, 4. Ja, I can also write it as r belongs to Zn. Simple, this value. Now to prove it is a homomorphism, 1, 1 as well as onto. So to prove it is a homomorphism, I take two integer r and s belongs to Zn. So what is f of r plus s? So this value is equal to a raised to power r plus s, this value a raised to power r, a raised to power s. So this is in multiplicative. So this can be written as f of r into f of s. So what it means? It means this map f, which is a homomorphism. What is this map? This is from Zn to G. So this map is a homomorphism. Homomorphism. Now next step is 1, 1 and third is onto. So there are 1, 1 as well as onto. Now first I take the element onto. So to prove the onto, I take one element. Let I take x belongs to G. So what is G? G is generated by A. This values. It means x element is a raised to power some r. And what is r? R lies between 0 less than equal to less than n minus 1. So if this kind, right? So just see the values. So what we get? We get x equal to a raised to power r, and this values lies between a raised to power r, and it means x is equal to ar. So this is equal to f of r. So where r belongs to Zn. So what it means? There exists r belongs to Zn such that f of r is equal to x. So it means this map is a onto mapping. So this is my second result. It is a onto mapping. Now also both have the same order, then it is a 1, 1 because it is homomorphism onto and order of G and order of Zn. They have n element. If they have n element and also it is onto, so it means it is also 1, 1. So since order of G and order of Zn, they are same, and f is onto, also it is onto, so it implies f is also 1, 1. So it proves all the properties. What is 1, 1 onto and 1, 1 onto and homomorphism? If it is 1, 1 onto and homomorphism, then this cyclic group is isomorphic to Zn. So this is of order n. If this cyclic group is of order n, then it proves our result. Also, we can prove 1-1 directly. So how we can prove 1-1 directly? So take f of r is equal to f of s. It implies a raised to power r, which is equal to a raised to power s. It implies a raised to power r minus s is equal to identity. So what is r? So r s less than n and greater than equal to 0, this values. So it implies order of a divide r minus s, right? So this means this is possible because r and s is less than n. So this is possible only if r minus s is equal to 0. So this values. So if r minus s is 0, then it implies r equal to s. So it also prove in this way because order of a, which is n. So n here, if n divide this, so n is less than r minus s. So there are only two ways. Either it is equal to n, that is not possible here, or it should be equal to 0. So that's why it is equal to 0. So r equal to s. Now from this also we conclude that if G is a finite cyclic group of order n. So we prove that G is isomorphic to Zn, and also we prove that G is isomorphic to Z by generated by n. So we prove these two things. Now since this is isomorphism is a equivalence relation, so this can also be written as Z by generated by n isomorphic to G. So from these two results, what we get? We get Z by n isomorphic to Z by generated by n. So this is my next result. So in examination, it may be asked in this way. So prove that Zn is isomorphic to Z by generated by n. So this is very important type. So we can also say that any cyclic group of n is isomorphic to additive group of residue class n. So also we can prove in this way. So this is my result.